All right, well, let's open with bear back. Work. Let's open with prayer. Lord, we thank you for this day. Father, thank you for the message we heard in chapel. Lord, the truth that our worth is not in what we've done for you, but in what you've done for us. Lord, that your heart is moved by faith, not by our works. Lord, as we study today about quantum mechanics and electron orbitals and shells and configurations and shapes and all these things, we do need to know these, but Lord, may we just have a sense of awe of the orderliness of the universe, of just what a mind, what a wisdom, what a power that can create all these things and hold them exactly in their place. How blessed we are to discover anything of it. We pray this in Jesus' name. Amen. Well, all right. We are kind of done with most of the math. Most of the math that we have is super simple. We're done with most of the math of this particular unit. Let's see, I put a check mark where we left off. Okay, sounds good. So there are some conceptual things that we need to be aware of for moving forward. They're going to affect stuff, and I don't even think you have to do. Yeah, you don't have to know most of this math stuff. So one thing is called the Heisenberg uncertainty principle. I'm spelling this right. Heisenberg uncertainty principle basically says it's fundamentally impossible to determine at the same time, simultaneously and exactly, both the momentum and the position of a particle. So you cannot, at the same time, know both the position and the momentum of a particle. Talked about how any particle that were to be moving in a trajectory, a more or less linear trajectory, absent gravity, absent other interferences, in what I might perceive to be a straight line, it's never actually moving in a straight line. Everything is moving as a function, as a sort of a wave function, right? Up and down and up and down. If I throw a baseball, at any given point in time, you take a snapshot, you figure you can know exactly which way it's going, what its momentum is, its direction, its speed, it's all that kind of stuff, but also exactly its position. And based on that, you can predict the next moment, exactly what its momentum and its position is going to be. With a large object, that's our very reasonable experience. But with quantum particles, things down at the atomic and subatomic level, that's not a reasonable thing to say because it's not our experience. If I can say exactly in a moment where an electron is, I cannot also say what its momentum is. I can't tell you the speed it's traveling, I can't tell you the direction in space, any of it. It's impossible for me to know both. I can know one or the other. The greater certainty I have of one of those two, the less certainty I have of another. There's some math associated with that. We can learn it, but it would just be another equation that then we're never going to use. So we're not going to learn that, okay? But if you were interested in that, it's on page, where's it at? Yeah, it's on page like 278 in your textbook, okay? I'm guessing you're not going to go there, but you know, you might get a wild hair. So this is the Heisenberg uncertainty principle. All this is relating to electrons, looking forward to electrons and where they're going and where they're at and how can I know? Because you, go ahead and look at me, this is your connection, right? It's virtually impossible to say what's going on with an electron. We can't speak of electrons and where they're at in an atom, or around an atom, or in a bond with any certainty. We can only speak to it with probability, okay? When we draw these things like this is grossly, you know, and then we go, okay, that's an electron. There's an electron going around that in that shell. No, not really. Like, this is a representation, just like a map is a representation or it's a model of some three-dimensional thing. It's useful, right? It gives you some sense of certain things on a scale that's manageable, but it doesn't actually tell you what the city looks like, right? It's not going to tell you, oh, there's a fire hydrant there, there's going to be a lady walking a dog, there's going to be rain, the buildings are going to be this high, you're going to get blind. It doesn't tell you those things. Your actual experience will be very different than this representation. Similarly here. This is okay, this is okay. Actually, this is even decent for the simple, like, for hydrogen and helium, this isn't too crazy. Now, you got to remember, this is only 2D, right? So you have to imagine this in 3D, at the very least. But then you have to remember that it's actually like a wave, right? Doing this. So it's doing this in like all directions, waving in and out all over the place. So I look like I'm having a seizure. But you can laugh, it's okay. But it's not bad. But once you get past hydrogen, helium, lithium, and beryllium, this breaks down quickly. And again, this is, at best, I'm telling you, there's a probability that it's like somewhere along like a circle or a sphere. But actually, it could be slightly one side or the other as it's waving and stuff like that, and I don't know exactly where on that sphere. So we have high degrees of uncertainty. And this is just looking to explain that to you. That's why it's worth taking a moment. I probably took too many moments to talk about that. All right. Now let's give you some other things. Yeah. Okay. We're going to talk about quantum numbers. Quantum numbers are going to describe predict the location, trajectory, the different aspects of an electron. Okay. Quantum numbers, write this down. Quantum numbers are going to describe electrons in an atom. We're going to have 4 of them. We're quantum numbers, okay? They're going to be these. N. This is the principal quantum number. It's basically going to define an energy level. We've been talking about electrons getting excited, going from a ground state, the lowest energy level, the first energy level, to a higher state. And so they have to absorb a specific quanta of energy from a photon to be able to do that. And when they fall back down from the excited state to the ground state, they release that exact same quanta of energy. Well, what we just said, as I described that, is it went from n equals 1 to n equals 2. And then it went from n equals 2 to n equals 1. So these n values, n equals 1, 2, 3, 4, 5, okay? Does that make sense? Each time we're having to add a specific amount of energy to raise up. Okay? Let's do our second quantum number. Second quantum number is L. This is angular momentum. Basically describes shapes. And this one is just n minus 1, right? Next one is magnetic quantum number. It's M with a subletter L. Magnetic quantum number. Refers to our orientation in space. It's going to be something like 2, 1, 0, 1, 2, etc. Whole integers, either side of 0. And then our last one is our spin quantum number. And this is basically in paired electrons. One spins up, the other spins down. That'll make more sense. These are the only possible values. It's either spinning up or it's spinning down. So we do, well, let me go back to this. This is how we tend to draw it. The reality is it gets written like this, either negative half or 1/2. I'm going to show you a video, and then we'll talk.
Let me show you how.
Now that we understand that electrons are both particles and waves, we are ready to learn about how electrons are arranged in an atom. The location and energy of every electron in an atom is determined by a set of 4 quantum numbers that describe different atomic orbitals. An orbital is a region of probability where an electron can be found. There are s, d, p, and f orbitals with different shapes, and they look like this. Remember, these shapes are not electrons, just regions in space where electrons can be, and each one can hold up to 2 electrons. The more electrons an atom has, the more of these orbitals it will need to accommodate them all. The first quantum number is the principal quantum number n, which can have any positive integer value. We saw this when we learned about the Bohr model. It represents the energy level of the electron. Each orbital will have an n value, and the larger the value of n, the further away from the nucleus it is. The next quantum number is the angular momentum quantum number, L. This can have any value from 0 to n-1. For example, if an electron has an n value of 3, it can have an L value of either 0, 1, or 2, because 2 is 3 minus 1. The L value describes the shape of the orbital. When L equals 0, we are describing s orbitals, which are spherical, just one of these per energy level. When L equals 1, we are describing p orbitals, which are lobes that extend outwards on 3 axes. There are 3 of these per energy level. When L equals 2, we are describing d orbitals, which are weird looking, 5 of these per energy level. And when L equals 3, we get f orbitals, which are even weirder looking, 7 per energy level. Next, we have the magnetic quantum number, m sub L. This can have a value of anywhere from negative L to L. So if L is 2, m sub L can be negative 2, negative 1, 0, 1, or 2. This quantum number determines how many orbitals there are of a type per energy level, and therefore describes a specific orbital amongst a particular set. When L is 0, m sub L must also be 0, and that's why there's only one s orbital per energy level. When L is 1, m sub L can have 3 values, which is why there are 3 p orbitals per energy level. An L value of 2 gives us 5 values for m sub L and 5 d orbitals, and an L value of 3 gives us the 7 f orbitals. The last quantum number is an easy one. It's the spin quantum number, m sub s. This one will be either 1/2 or negative 1/2, no matter what. So every electron in an atom has a unique set of quantum numbers. No 2 electrons in an atom can have precisely the same 4 quantum numbers, as is stated by the Pauli exclusion principle. This is because any orbital can only hold up to 2 electrons, and even the 2 electrons in the same exact orbital will have opposite spin values. So let's try to describe different sets of quantum numbers and what they mean. When n equals 1, L must be 0, and m sub L must also be 0. That means we are describing the 1s orbital. It can accommodate 2 electrons, which will have spins of half and negative 1/2, respectively. This is the lowest energy orbital, so any atom on the periodic table will fill this orbital first. The electrons in hydrogen and helium occupy this orbital since they have only 1 and 2 electrons respectively. When n equals 2, L could be 0, which would give us the 2s orbital, or L could be 1, meaning m sub L could be -1, 0, or 1, giving us the 2p orbitals. The outermost electrons in the second row of the periodic table will occupy these orbitals. When n equals 3, L could be 0, giving us the 3s orbital. L could be 1, giving us the 3p orbitals, or L could be 2, giving us the 3d orbitals. A large atom will have to use all of these orbitals and more to house all of its electrons. The Aufbau principle tells us the order in which an atom will fill up its orbitals. This is determined by their...
We're going to pause there. Come back to this in a minute. Okay. You have this? I'm going to erase this. We're going to do a little drawing and try to make this make sense. If you have a periodic table, please get it out. If you don't, let me know and I'll hand you one here in a second, okay? Gotcha. So we're in this file. Periodic tables. Who's got a good periodic table and go make a copy of it? Be right back. Thank you, man. Okay. Take a look at hydrogen, okay? How many electrons does it have? One. Right, so I've got a single proton here in my nucleus, right? I have an electron, let's say in its ground state, its normal state, right? My principal quantum number is 1. It's going to be in the first shell, okay? So here's that electron. L, angular momentum. Well, this begins to describe shape. My electron here, roughly speaking, orbits this thing as a sphere. Okay, you got to remember this is three-dimensional. But this is it. It's going around as a sphere. That shape is defined numerically as n, the principal quantum number, -1. So in this case, it's it's L equals 0. Okay, and this is telling me basically that this is a sphere. Okay. My magnetic quantum number here is going to be 0. It cannot be greater than my than n-1. Is that right? I believe so. So m1 equals 0. Now, this spin quantum number, ms, in this case it can be one or the other. What I'm saying is, so each of these electrons spins like a top. They're just spinning, spinning, spinning. in every subshell, you can only fit 2 electrons. Okay, because they repel each other. It's called Pauli's exclusion principle. And so it'll get kicked off to another shell somewhere. Well, once all of the shells have 1, then you can begin putting another electron in. But that electron cannot have the same spin. If this one's spinning this way, let's see if I can do this, then this one has to spin this way. They'll look like they're spinning in opposite directions. It's just that one's up, one's down. And this just has to do with the interactions of the electromagnetism, et cetera, et cetera. So this can either be +1/2 or -1/2. I don't know which, okay? If I did, so this would be true for hydrogen, okay? If I were to do helium, well, my N is still 1, right? I only have 2 electrons. I'm in the first energy level. My shape is still N-1, so it's still a sphere. My M1 is still 0. But now I don't have MS equals +1/2 or 1/2. I have both. So I have 2 electrons here. One is spinning. One is oriented up, one is oriented down, one's spinning this way, and one of them spinning this way. Does that make sense? This describes these 2 electrons in helium with the greatest detail that we're capable of, okay? No matter what quantum number we have, we will have a shell that looks like this, that functions like this. So let's do lithium, okay? Lithium has its atomic number what? 3. So I'm going to have 3 protons, right? How many electrons? 3. Where's my first electron go? The first shell. Where's my second electron go? In the first shell. Now that I have 2 in the first shell, that first shell is full. So the next one goes to the third shell, or to the second shell, right? So this shell doesn't go anywhere. It's still here. It's always here. I don't care what atomic number you have. Once you get past helium or hydrogen, they all have this first shell. It's just inside. Now, that's why we talk about the valence shell. Those are the ones that are doing all the action, right? They're the ones that are bonding and doing ions and all this. But this is always here. And it actually plays an important role in some of what we see later. For lithium, I have this, and it's out here, and it is also doing this sphere thing, right? Well, I can describe the 2 inner electrons. I already did it. The things that were true for hydrogen are true for helium. They're true for lithium. They're true for polonium. They're true for all of them when we're talking about the first 2 electrons. I'm interested in the valence electrons, right? So out here I've got 1 in my valence shell. So let's talk about that. So my principal quantum number is 3. N equals 2. I'm in my second shell. Good. For that second shell, angular momentum equals N-1, right? So 2 minus 1 is 1. Okay? Now, this means at this stage, I can still have a spherical shell, but I can also have what we refer to generally as dumbbell-shaped shells. Okay? This L, well, we'll get there in a minute. M1, my magnetic quantum number, is my orientation in space. I can have positive integers up to N-1, and I can have 0, right? So N-1 is 1, and I can have 0, and I can have opposite of that. These are my magnetic quantum numbers. Here's what that means. By the way, this is called an s orbital right here, okay? And this is also. This is an s orbital. The first shell, the spherical shell is the s orbital. Do you guys remember hearing that from high school, maybe? A million years ago? No? Okay. All right. Well, that is what it is. This dumbbell shape, so these are my s orbitals, these are my p orbitals. Well, an s orbital in space, because it's a sphere, it's just a sphere. Right? Like, where are you at on the sphere? It doesn't matter. But these, take a look at something like this, right? This would be basically the shape of a p orbital. Well, I can have a p orbital in 3 dimensions. I can have it this way, I can have it this way, and I can have it this way. Does that make sense? If I'd have planned better, I'd have brought some balloons today. But I actually plan to bring balloons next time. Because we'll do some of this kind of stuff. Here's what you need to know. If I took a single balloon and I just blew it up, roughly form a sphere, right? But if I put 2 of those together, it's going to form this shape. And if I put 2 more of them together, it's going to be forced into shapes going this way. And if I put 2 more of them together, I don't have one here. Well, it'll stick. Maybe I can force it. Let's see. See what I can do. That's not bad. That's not bad at all. You put 2 of these together, you get kind of this shape, right? And if I have another one, it's not going to work out very well. But you get the idea. We're going 3D with this. I got lobes going all these different directions. That each of these is referring to a magnetic quantum number, an orientation space, right? So for my p orbitals, I can have 1 or 0 or -1. One of them's going to send me this way, one of them's going to send me this way, one of them's going to send me this way. That's all we're describing when we throw those things out there. So here's what this matters. So you remember drawing something like this? I haven't done this in a million years. My goodness. About like that. Like to do axes in space 3-dimensionally, right? So if I have a sphere, like it's just, here's my sphere. Like, okay. But now I go to my p orbital, so I got a sphere, right? But I've also got a lobe operating here, and I've got a lobe operating here, and I've got a lobe operating here, 3-dimensional. Okay? Capiche? Sure. So that's why it's saying an orientation in space. With the P's, I've only got 3 orientations. Okay? They're going to operate at 90 degrees to each other. Okay? So, that's where my M number comes from. My MS is still either going to be +1/2 or -1/2. Well, for lithium here, if I'm actually trying to physically describe this electron in lithium, okay? Well, this is N equals 2, L equals 1, M equals 0, because is that what I want to do? I'm going to stay away from that right now. Come to that in a little bit. Let's go to, let's do fluorine. Fluorine's good. Atomic number? 9, right? Okay. How many electrons? 9. Where did the first 2 go? The first shell, right? What shape are they in? Are they S's or P's or D's or F's or what are they? They're S's. They're going to be in a sphere. My next 2 electrons, where are they at?
Second shell.
In the second shell. Okay. So I've covered 4, and they're also in an S shape, right? They're doing a spherical thing. Okay, now let's deal with the next 5, right? Is that right? 5. Okay, so what happens here is we begin to fill these other shells. So my shells are going like this, right? And they're going like this. And I've also got one that's going to kind of go like, you know, perpendicular here. It's going to go like this. I'm not drawing a 3D very well, but you get the idea. So what happens here is they'll begin to fill. I'm getting ahead of myself and teaching Pauli's exclusion principle. I'm actually kind of meshing like 5 different things. Because they are meshed in my head. So, you know, the book will tear them apart. I've already got 4 of my 9 electrons accounted for, right? They're in those spherical suborbitals. Now, I need to go electron here. That's 1. I need to go electron here. That's 2. And then I need to go an electron here. That's 3. The charge on electron being negative is such that if I try to put another negative next to it, they repel each other. It's going to kick it as far away from it as it can. As far away from it as it can is not the other side of its own orbital. It's actually, or its own subshell. It's actually one of these other subshells. So for the p orbitals here that look like this, I need to fill each of those p shells with 1 before I put a second one in any of them, okay? So I will get 1, 2, 3, and then I can go ahead and add 4, 5. Oh, this doesn't get 6, right? It's got room for 1 more, right? We'll think about fluorine. Fluorine with where it's at on the periodic table, right? It's very, very likely to form an ionic bond, right? It wants to pick up 1 more electron and put it right here. Creates stability for it. Okay. So, for the electrons in fluorine, right, we know that N equals 2. We know that L equals 1, which means we're in this dumbbell shape. I know that my magnetic spin number is -1, 0, or 1, correlating to relationship in space, right? We can either be in this dimension, or in that dimension, or in that dimension. And each individual electron is either spinning up or spinning down, right? They'll all fill halfway, spinning up, and then they'll begin to fill halfway, spinning down. So I could talk about each and every one of these electrons individually. And this is great. What we just taught you right here will take you through to element, well, the scandium really. And then we get big. We get too big. We've got to add other orbitals. All right. I think that's good for right now. Let me check the book stuff, make sure I haven't missed anything that you're going to need. What time is it? What time did we get out of here? About 2? Almost 2? 1:50. Okay, good. We got time. Good, good, good. Okay. So we're talking about these quantum numbers. Indicate the number of subshells, the number of orbitals in each subshell, and the values of L and M1 for the orbitals in the N equals 4 subshell of an atom. So here's what it's asking us, what we want to be able to do. So for N equals 4, and we want to find the L value, and we want to find N1 value, or N sub L value. Okay, so N equals 4. What number do I already have? What is that on all this? It's my principal quantum number, right? So everything else is going to play off of that. If my principal quantum number is 4, right, then what are possible values for L? Well, it's N minus 1, right? For this one. So I can have 3 and 2 and 1 and 0, right? So I can have values of 3, 2, 1, and 0. Okay. That's good. Oh, goodness here. Okay. What is this? Indicate the number of subshells. Okay. So how many subshells can we have out of this? This is weird. It's a weird question, a weird way to ask it, and a weird way to answer. For n equals 4, L can have values of 0, 1, 2, and 3. Okay, great. Thus, S, P, D, and F subshells are found in n equals 4. Well, that fits. 0 is S. This is P. This is D. This is F. I know we didn't talk about those yet, but that's okay. They're different shapes that these things form. Okay. Thus, S, P, D, and F subshells are found in the n equals 4 shell of an atom. For L equals 0, the S subshell, M1 can only be 0. Well, okay, good. Thus, there's only one S orbital. Oh, this is how they're answering this. I get it. Okay. Yeah, where they're going. So, for the S1 here, all right, to determine this value, right, if this is 0, then this can only be 0, right? So I've got one option. But if this is 1, right, then I can get values of 1, 0, and -1, right? And if this is a 2, then I can get values of 2, 1, 0, -1, -2, right? And for my F, for 4, I should be able to get 3, 2, 1, 0, -1, -2, -3. Let me make sure that is what they're saying. Thus, there's only one enforcement for L equals 1. P type orbitals, M can have values of -1, 0, +1. So we find 4 P orbitals. For L equals 2, the D orbitals, M1 can have values of -2, -1, 0, +1, +2. So we have 5 of those. And when L equals 3, the F-type orbitals, M1 can have values of -3, -2, -1, 0, 1, 2, 3. And we can have 7 F orbitals. Thus, we find a total of 16 orbitals in the n equals 4 shell of an atom. So let's count that up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Why are you asking us this question? Not entirely sure. But there it is. Sub-question here. Identify the subshell in which the electrons with the following quantum numbers are found. This will be more fun. So it's going to give us these quantum numbers. N equals 3, L equals 1. Okay, so if N equals 3 and L equals 1, Let's think about that. What energy level am I in here? Got it? No. Got to be in the third energy level, right? So third energy level. And my L equals 1. Well, okay, so what is it wanting to know about that? Oh, it's, okay. What shape is this, if L equals 1? It's the P ones, right? It's a dumbbell shape. So all it's wanting out of this is for you to say, oh, this is a 3P subshell. That's all that's wanting. Okay? I don't think quite like them, so here we are. The next one they ask is for n equals 5 and L equals 3. Well, what energy level? 5. What shape? If it's 3, take a look at it, right? It's 1. I'm sorry, that's 0, 1, 2, 3. Right? So these are S, these are P, these are D, these are F. So which one is this? It's 1F. Or I'm sorry, this is a 5F. Is that what I have us on here? Does. Okay, we're doing good. And last one to check this is n equals 2 and L equals 0. 0 is easy, right? What shape? S. Spherical, right? So this is 2S. Good. The purpose of that exercise, I think, was to equate this number always to the energy level and this to the shape, or the name of the shape. Okay. All right. Calculate the maximum number of electrons that occupy a shell. Here, I can erase this and try this. Calculate the maximum number of electrons that can occupy a shell with n equals 2. So if n equals 2, how many electrons can this guy hold? 4. 4? Okay, let's see. So if n equals 2, then we're talking about the second energy level, right? Okay, so what is the, if n equals 2, what does my L equal? It can equal either 0 or 1, right? Right, the 0, the S's. So this is S, and this is P. How many subshells for S? Just the 1, right? How many electrons does that hold? 2. So I've got S equals 2. P has how many subshells? 3, right? That one, that one, that one, right? Each of those can hold 2, so how many can P hold? 6. So my total, 8. Let's see if that's what they have here. That's what they did it. It is. Good. Okay. Now let's do the next one. It's going to do n equals 5. This is going to be a whole other thing. Okay. So if n equals 5, then L equals, pardon? 4. So we've got, and so my magnetic quantum numbers are going to be, what? 4, 3. I got 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4. Is that right?
I have a question.
Yes, ma'am.
For the M1, will it always go from the L number to the negative? Like, so if it's 4, it'll always go to negative 4. If it's like 2, it'll go to...
You talking here?
Yeah. No. Quantum. Magnetic quantum
Okay.
numbers.
So ask the question one more time.
So will it always go from like that number's value to the negative? Okay.
Yes,
Okay.
yes, in whole integers, yes. Okay. Okay, so my shapes here are I've got S orbitals, I've got P orbitals, I've got D orbitals, I've got F orbitals, and I have G orbitals, okay? This one has how many subshells? 0. 0 subshells. Well, I guess we can say 1. I'm sorry, let's say 1. Doesn't get defined. 1. This one has 3. This one has? Well, let's look at it this way. If I do, so this is this because it's my only magnetic quantum number I have for this orbital is 0, right? So that's 1. But here I have negative 1, 0, and 1. So that's where I get my 3. Here I have negative 2, negative 1, 0, positive 1, positive 2. And so this is 5. Here I have negative 4.
7.
Yeah. And then this last one? 9. Good. And so the question here is what? Calculate the maximum number of electrons. Okay. Good. So each of these can hold 2 electrons, right? So this is 2, 6, 10, 14, 18, right? So I just need to add those up. So that's 20, that's 30, that's 50. Is that right? Should be right. 50. Good, I can do math. Good. All right. You guys see why that is? Even as I'm kind of backing into things, so it's funny. Okay, let's do the next one. All right. So my last one is it's a variable one. We're still let's see. Okay. If a shell contains a maximum of 32 electrons, what is its principal quantum number? Okay. So the most it can hold is 32 electrons. It has 32 electrons, I know it has 16 shells, right? Subshells, right? Does that make sense? Because each subshell holds 2. So I know it's 16. So let's just think through this. S holds 2, right? P holds 6. D holds 10. I'm doing electrons, aren't I? Oh well, I went backwards. That's okay. I'm trying to find 32. So right now, they're getting me up to 18. F holds 14? Yeah. Okay, so what is that? That's 16 plus that is 22, it's 32. So I've got up to an F, right? So this is, my L here would be 0, 1, 2, 3. right? And since L is n minus 1, then this is 4, right? So this is, my n has to be equal 4. Questions of how there are other ways to get there. This is how I got there. I like to just count. Like, this just makes sense to me. Thoughts? Questions? Okay, that is the right answer, so that's good. All right. What time is it? It's 1:32. Good. Let's try another. They got 2 more problems that we want to look at. I may have to go back and teach you something that I've skipped because I didn't think it was that important. Okay. Okay. Complete the following table for atomic orbitals. Got an orbital. Have an N number. Have an L number. N1 degeneracy, which I have not covered, and radial nodes, which I have not covered. Okay. So I'm going to go back and teach some things that I skipped. That's okay. So our first one is 4F. Next one has N equals 4 and L equals 1. The next one is N equals 7, degeneracy is 7, radial nodes is 3. And the last one is 5D. You want to get that copied. That's enough. Okay, concept of nodes. Y'all are still doing that's worth writing down. I'd write it down. This will be the last thing we do today. We'll, once you're done with this, well, do this, and I assume there's going to be a follow-up problem. But once we're done with this, we'll definitely be done for the day. We'll pick up next time where we left off on that video with off-bout principle and stuff like that. Okay, so the idea of a node is a location where something cannot exist. So if I were to look at hydrogen and its electron in its first energy level, right? What shape is that? What's it named? S. S is a sphere. It's a perfect sphere. There is nowhere on that sphere that that electron cannot exist. Okay? None. So for the S orbitals, then there's 0 nodes. Well, that's because n equals how many? 1, right? N equals 1 minus whatever my L is. Well, L is n minus 1, so that's 0. So it's 1 minus 0 minus 1. So my s orbitals have 0 nodes. Okay. Now let's go up to n equals 2. Okay. Back to this. I want to make sure that I'm hitting this the way that it needs to be. N equals 2. We're going to do that. Okay, so we're going to do, this is a 2s orbital, okay? My n number is? 2. 2 minus, what's my L number? 1. Good. Minus 1. Right? I've got to go back and look at this. There's something in their description of this formula that's not clicking for me. I'm not sure how I see what they're getting, I'm not sure how they're getting it. And if I don't get it, I can't give it to you. That's going to be a mess. So we're going to stop here. I'll have this figured out for next class. That or we'll just skip it. If ultimately I didn't think this was important to begin with, I still think it's not important, but we'll see. Okay, there it is. Okay, let's do a quick, I'm pretty sure you've got all this, but I want to make sure. If an electron's in the 5th shell, what's its in number? 5. If it's in the 4th shell, 1st shell. Right? So all that in number is telling you how far away from the nucleus is it. Right? So it's in the 1st energy level, it's in the 2nd energy level, it's in the 3rd energy level, it's in the 4th energy level. The L, or I'm sorry, the L. L is going to tell me subshells, right? So if I'm in the first one, I have no subshell. All I have is just that one S, right? But now I go up to the second one, right? I've still got my S. How many subshells do I have for my other? Yeah, 3, right? So, and what is that one called? What shape is it? What shape does it make? Can you see it in your head? It's called P, and what shape is it? It's a dumbbell shape, right? It's doing this. Okay. Now I go up another level still, right? The shape is much more complex. What do we call it? D7. And then the next one we'd add, and each one has what, so you're always going to have 1s orbitals, always. I don't care what atom you are. Once you get to lithium and beyond, you have 1s and you have 2s, right? You got a sphere in the first sphere, you got the second sphere. After you get past the second sphere, now I've got to start putting in these dumbbell orbitals, right? So I've got to start putting in my 2p's, right? So you go 1s, 2s, 2p. Then, once I go past that, I've got to put them in that next orbital, right? So now I've got 1s, 2s, 2p, and now I have 3 what? 3s. Good. Okay. Now, after I fill 3s, I go to 3p. And then from 3p, I go to 3e. Right, good. Okay. How many suborbitals are there in S? It's just the one, right? It's just the one thing. How many in a P? 3. How many in a D? 5. How many in F? 7. Those keep going up by 2s, right? Good. How many electrons fit in each of those subs? 2. So how many can fit in an S shell? 2. How many can fit in the P shells? 6. How many can fit in the D shells? 10. And in the F shells? 14. From 5 to 14, right? So we go up by 2 and then double that. Good. Okay. We'll pick up there next time, and we'll also look at how do we know which ones get filled first. We'll look at some other things. All right. What is today? Wednesday. So I won't see you guys until next week. Next week we have a test?
Next one.
Goodness. Okay. If you need something, text me, call, whatever, get a hold of me. All right?
Have a good weekend.
You too.